questions? All right, so if you're looking at your slides, I'm going to save the last 5 slides for Monday. We're just going to do some more using delta H equations, rearranging them, and then we'll cover what was left in my little packet. We'll save Hess's law and pizza formation till Monday.
So that won't be on the
It will not be on the exam. Hess's law. I deleted them. Take that back. There's a little bit, there's like intro to Hess's law, which you can already do, but like the main Hess's law stuff, I moved to after Thanksgiving. And it's mostly on there because you use it in lab. Hess's law is in lab. All right, so using delta. So let's say, you guys seem like you're ready for the challenge questions. We'll do that one. We'll see. You may prove me wrong. All right, so I want to find the delta H reaction for this dinitrogen oxide and nitrogen dioxide makes 3 nitric oxides. And we're given the following equations. All right, so this is the equation I want, and these are the 3 equations I have. I'll wait for everybody to catch up with me. All right, so I have 3 equations that I need to recombine in some way to get the one I want. And so I know I want this dinitrogen oxide as a reactant. So which equation should I use that has dinitrogen oxide in it? 1, 2, or 3? 3. Right, this has N2O and that has N2O. This has N2O. Is it on the right side of the arrow, the correct side of the arrow? This guy, right, this is on the correct, both of them are on the reactant side, right? This is on the side, the right, left. It's on the left side, the correct side. I don't want to use right because it's the wrong. It's on the correct side of the arrow compared to this. Yeah? So I'm just going to, so if I do this. So I'm just going to rewrite it. All right, so now we've used that equation. What is the main issue with the way that this dinitrogen oxide is compared to this one? It's double how many I need. So how do I correct that? Divide everything by 2. Right? So if I divide everything by 2, this is now a 1. This is now a 1. What happens to this guy? It is a 1/2. Don't let that panic you. It's okay. What happens to my delta H then? Also divides by 2. Does it change the sign? No, right? Just divide by 2. All right, so we're well on our way. Let's take a look at, what do I want to do next? This NO2. I want that as a reactant. Do I want to use equation 1 or equation 2? Equation 1, right, because that has NO2 in it. This reaction has it as a reactant. This one has it as a product. Right, so now I need to write it the other direction.
Wait, can you do that though?
Sure.
Because now
I switched the sign. Right, so I've written it in the opposite direction, so the sign has to change. So before it was exothermic, now it's an endothermic reaction. I haven't changed the value of it. But let's take a look at how many I need. Up here I only have 1. How many do I have down here? 2. I need to do the same thing, right? So I need to divide this also by 2. So I only want 1, now I have 2. So I'm going to change that to a 1. Change this to a 1. Make that a 1/2, then divide that by 2. All right, now, right, I've used 1 and 3, so it's all I'm left with is number 2. Does it make a product that I want to make? Is that the thing I want to end up with? Yeah. So the nitrogen and the oxygen, right, there's nothing for me to use, so I'm just going to assume that I'm going to leave it as is. So I'm going to rewrite it. All right, so we've used all 3 of our equations. So now we need to double check to see if we've made what we want to make as our final reaction. So what is one compound that I can cancel out on both sides of an arrow? The N2, right? I have N2 going in, and I have N2 coming out. Question first?
Sorry, I must have missed this. Why did we change the 2? Because I know it says 3 NO.
Oh, we haven't gotten there yet.
Oh, okay.
That's the one I want to make. I have to use these guys down here, so that's the 2. Right, I just rewrote this one down here.
But since like we changed all the other,
Oh, look, if I have 1, I have 3. I have 3 altogether right down here. All right, so we're going to, once we cancel some of these guys out, it'll be easier. So the N2s are gone. What else is gone?
The O2s.
The O2s, right? I have 1 on this side, and I got 2 halves. And they're all gone. Is there anything else that cancels out? There shouldn't be. Nothing else should cancel out. So I should have N2O plus NO2 makes 3 NO. Oh, okay. So I like these because they're kind of like a puzzle. Right, because you can kind of logic your way through them and then things cross out. All right, so how do I figure out the delta H for all this stuff? You just add them all together. So I got to do negative 163.2 divided by 2 plus 113.1 divided by 2 plus 182.6. How many significant figures do I get?
4.
I get 4. All right, so this reaction is a plus 157.6 kilojoules. Is that endothermic or exothermic? It is endothermic, so where is the heat going? Into the system. Yes. That's as tricky as they come. They definitely won't be that tricky on the test. It should be hopefully a little more straightforward. Then again, I like these. So they make sense to me. So I try to dial it down a little bit. So, questions on that? All right, that's all the new stuff I had. We'll save everything else, chapter 6, for later.
But so that is not Hess's law?
That is not Hess's law, no. Hess's law is what you're doing in lab, where you use the heats of formation, and you do products, mass reactants. That preload question you just asked me about, that's Hess's law.
Will we have to memorize those numbers in the back of the book?
No.
Okay.
That'd be a ridiculous number of numbers to ask you to memorize, so no. All right, questions for me to go over? Yeah. Number 9? Sure. Let's see, number 9. Oh, first of all, the answer key is wrong on number 9. Yeah, number 9, the answer key is totally wrong. My copying and pasting got a little away from me. All right, so number 9 says, give the net ionic equation if you put in potassium sulfate and baric nitrate. The answer has nothing to do with carbonate. I don't know what happened there. Got a little away from me. So yeah, typo on that one. Do you want me to do it anyway? No.
Wait, can you say the answer one more time?
The answer is, it should be Fe2 plus S minus 2 equal, or arrow, FES solid.
Yeah.
That should be the answer.
It's going to be like that on the test, right? Easy.
I mean, sure. Nothing? You guys got it? Yeah.
Do we need to know the gas evolution reaction?
If you need them, I'll have to give you those because we haven't covered them enough. Do you just want me to pick random problems?
Okay, this doesn't have the same numbers that the one that one just had.
Okay.
But it's number 10 on this first one.
Let me see.
Okay.
It's number 1 now.
Oh.
All right, number 1. Which of the following substances that have their specific heat given have the greatest temperature change upon absorbing 100 joules of heat? So to make this easy, I made them all the same mass. So what we're going to do is we're going to think through what the answer to this is.
And all the stuff at the top that said it got was the honor test given to us?
Yes, yep,
Okay.
yep. All right, so the question is, if I have given you specific heat, what is the equation you need to use? Mm-hmm. Right, so the word specific heat in the word problem should tell you, oh, this is the equation. All right. So, which of these variables am I looking for in this question? I'm looking for the delta T. Right, so for all of them, they all have 10 grams, right, so the mass is all 10. Where do I put this 100 joules of heat? Q. So all of them will look like this.
Will Q always be joules?
I mean, it could be kilojoules,
Oh, okay, well.
but yeah.
So that means if it's in kilojoules, you just have to put it in.
Yeah. All right, so all of them are going to look like that. So the question is, we have a few different options for CS. So what I'm going to do is I'm going to plug in one, see what it looks like, and then we'll think through the rest. So let's do, I guess, A. We'll look at A. If it's 100.0 equals 10.0 times 235 delta T. All right, so the delta T of that, what is that? 10 times 0.235. All right, so the change in heat for silver is 42 degrees. So the only thing I'm going to change is this number right here, right? So what if I made this number bigger? How would delta T have to change? You would have to get smaller, right? So if CS is going to be anything bigger than 0.2, the delta T is going to get smaller. So automatically, B, C, and D are bad choices. Okay, what if, is there a value that is smaller than 0.2 as a specific heat? This guy, right? So if this one's smaller, then delta H must, or delta T must be bigger. So done. E is the right answer.
Wait, inverse.
Mm-hmm. Yep. Right. For this to equal 100 every time, these two must go opposite directions. So you could have certainly solved it 5 different times and gotten 5 different answers and then picked out the right one. That is the long way to do most of these problems. Most of them you can just think through what it is. So E, number 1 is E. Jasmine. Mm-hmm. Yes. Yep. All right, other questions?
Number 3.
Oh, that's my favorite. Yes, definitely number 3. All right, number 3. All right, so number 3 is a calorimetry question. All right, so I have fructose being combusted to make a sample, to change the heat capacity of this question. All right, so this is a reading comprehension question, really. All right, so it's saying the heat capacity of the calorimeter is joules per degree Celsius, and you have a temperature change. And the previous one, I gave you specific heat capacity, right, which is C little s. And this one, I gave you heat capacity. So what is the difference in the equations? It's just C delta T.
And what would C be?
Heat capacity.
So unless there's an S on it.
Or I use the word specific, which means little s. So it's either heat capacity specific or just heat. So the trick to this one is I only gave you the heat capacity. which the units should be a giveaway, right? These units were in joules per gram degree Celsius, and these units are in joules per Celsius. So no mass. Which I think means something in Spanish. No mass, no mass. Anyway, yeah. Doesn't mean that in chemistry. All right, so then we're going to find Q at the calorimeter, CAL. Plug this in, 2.115 times 10 to the 4th. All right, the temperature went from 23 to 27, so should I have a positive or a negative delta T? Positive. So that's going to be 2.115. How many significant figures do I get? 3.
This for A?
Mm-hmm, this is just A. Oh, that should be a 3, sorry. One, two, three. Oh. All right, so you get 89 kilojoules. I didn't specify joules or kilojoules, so both are fine, either one. If I specify, then use that one. But if I don't, All right, so that is the Q of the calorimeter. What was the reaction that I was looking at in this word problem? Fructose combusting. So this is A. So what must be the Q of the reaction? Mhm.
Can you say how you do that again?
Sure. This was Q of the calorimeter, which is not the reaction. That's the surroundings. So the Q of the reaction has to be equal and opposite. Equal number. This is.
Or so you're saying that by the negative, that the surroundings gain.
Mm-hmm.
Is it left the same?
Mm-hmm.
It's okay if I put this back in kilojoules?
Sure. Mhm. All right, so that's A, that's B. So then C asks, what is the Q of combustion for 1 mole of fructose? All right, so did I combust 1 mole? Do you know? You don't know. I combusted 4.5 grams. How do I find out how many moles that is? Convert it. So 4.5 grams. Happens to be fructose and glucose are pretty much the same molecule, so it's still 180. What's that? 4.5 divided by 180. No, 0. That's a 2. That's an out of control 2. It's a real serious 2. 0.02 moles. All right, so if this is how much I combusted for just this little bit of moles, how do I figure out per 1 mole? Divide. What do you mean? Isn't kilojoules per 1 mole, or just kilojoules?
So it's just how many kilojoules in that mole?
Hmm? Yep. Which makes sense, right? I gave off 89 kilojoules when it was a little bit of a mole. So if I have a whole mole, I would expect it to be way, way, way more kilojoules, which it is. It's like, what is that? 4,000 and some kilojoules.
So it's just
Yeah, the textbook's kind of weird about it. Sometimes it's kilojoules per 1 mole, and sometimes it's just kilojoules, so. Yeah. The 1 mole is sometimes assumed. So. Other questions? I can do some random problems.
And the oxidation was
Number 11, but I don't know if the calculations required to raise the temperature one.
Calculate the heat required. Oh, number 2. Okay, 2. All right, so the question is, calculate the amount of heat required to raise the temperature of 79 grams of a sample of ethanol this many degrees. Is that in focus at all? I do. Oh, there we go. All right, so calculate the amount of heat in kilojoules required to raise the temperature of 79 grams of ethanol from 298 to 385, given the specific heat capacity. Mm-hmm. So the question is, I have it up here too. All right, so degrees Celsius is equal to Kelvin degrees, just off shifted, right? 0 Celsius is 273 Kelvin. If I'm at 1 degree Celsius, I'm at 274 Kelvin. 2 degrees Celsius, 275 Kelvin, right? It's the same amount of degrees. So the difference in Kelvin is equal to the difference in Celsius. You could certainly convert both of these to degrees Celsius and then find the difference. Or you just take the difference, because it's the same, and then plug it in. So this would just be 79.0 grams times 2.42. And whatever that is, 298. Oh, no, other way. 385 minus 298. So again, a lot of these problems are real straightforward once you read what they're asking for. All right, because that seems like a really long problem, but you just need to plug it in, multiply them by each other. Anything? Nothing? 6? Let's see. 6. Oh, 6 you can skip because that's Hess's law.
Okay.
So 6, I thought we'd get to, but we didn't. So 6 on the practice test you can skip. I can certainly show you how to do it.
Can we replace some of these hard stuff with Hess's law?
What are you talking about? There's nothing hard on here. Titration, limiting reagent, net ionic equation, precipitation, complete ionics, titration. Yeah, no, you're fine. Yeah, Jasmine.
For number 10, is so reduced by timing one that's not soluble.
Correct. That's all I'm asking. Which one is not soluble of this list? Which one's not soluble? Which, in your head, if you're thinking, all right, well, 2 of these have sodium, that's for sure soluble. And carbonate is always soluble. So, D, done. So, anything with sodium in it, always soluble. Anything with carbonate in it, always soluble. D, not soluble. 8? I certainly will. That's one of my favorites. Number 8. All right. Let's see if I can get it to be less pink and fuzzy. right, so the question 8 is what volume of silver nitrate is required to react exactly with 155 milliliters of 0.274 molar sodium sulfate? And you have to write your own balanced chemical equation. All right, I can give you a hint to get started.
Do we have to include the states?
It will be helpful. Yeah, that's it. That's the hint. Those are definitely the two reactants. All right, so for every single time we've done this, what do we do to predict the products?
Switch partners.
Switch partners. So let's think through, what is the charge of nitrate always all the time? -1. NO3 is always -1. So if that's -1, what must be Ag? +1. All right, what is the charge of sodium all the time, always? +1, and I have 2 of them. Right, so overall it's going to be +2, so what's the sulfate? -2. All right, so one of them is going to be silver sulfate. But what do I need to do to make the silver sulfate? 2 at the big here? No, oh, okay. Okay. So I've made a silver sulfate, so what must be the other one? Okay, is this charge balanced? Is the whole thing mass balanced? No, what's wrong with this? Right, so I have 2 sodiums on this side, but only, okay, so if I do 2 over here, then I need 2 on this first one. Now you're ready to get started. Oh,
Wait, which one's the solid? States.
excellent. Which one cannot possibly be the solid? Sodium can never ever be a solid. So by process of elimination, who is a solid? That guy. All right, so now we're ready. Once you've done this, now it's just kind of a titration question, right? So I want to know what volume of this is required to react with that. So of all the pieces of information here, where should I get started? Start with the milliliters. Yep. Do you guys need to convert that to liters? You can do that in your head. Feel pretty confident about that? Okay. All right, so I'm in liters of sodium sulfate. I want to get to moles of sodium sulfate, so how do I use the molarity? Multiply. Do I put the 0.274 on the bottom or on the top? Top. I tried to trick you. All right, now I'm in moles of sodium sulfate. I want to get into moles of silver nitrate. Now what? Mole ratio, so what do I put on the top? 2. All right, now I'm in moles of silver nitrate. How do I get to liters? I use the molarity. So I put the moles on top or on bottom this time? Bottom. What is that? Turns to be 0.155 times 0.274 times 2 divided by 0.305. Sure. It doesn't say, so either one would be fine. Yeah. You could leave it in liters. You could choose to convert to milliliters. If I don't specify, just leave it. I'd say move on to the next problem. Unless you're real obsessive about, well, I put in milliliters, I need to get out milliliters. Usually when people do that, they make an error in that very last step. And they end up telling me that that's like 2 milliliters or something, and they're panicked, right? They're trying to move on. So if I don't say, just... Yeah, it just depends. Like if it specifies, then do that. If it doesn't specify, then just.
I just have a quick question.
Yeah.
Okay, so if it says a complete ionic
Mhm.
equation, we don't have to find, like, we don't have to get rid of the spectator.
Correct.
Make sure.
Yep. Net ionic, no spectators. Complete ionic with spectators. Molecular would be this. The whole thing written all together.
Will we ever have to balance a complete ionic equation, or will it be balanced before?
It would have to be balanced before. Because it's hard to put them back together if you don't know where it came from. So. You guys ready for Friday? Feeling confident? You got 48 more hours.
With another thing, sorry.
Yeah. Question first?
Oh, no, I was
Oh.
just starting around and making home Monday.
Oh, yeah, that's not going to happen.
Yeah.
Yeah.
So,
Yeah. Anything else? You guys feeling confident? All right, I do have office hours tomorrow. If you need them, I'll definitely be there most of the time. I can't guarantee I'll be there the whole time because anytime I do that, I've wandered off. If my door is open, I have not gotten too far. If I've closed my door, I've gotten far away. So if the door is open, I'm bound to boomerang. I'll come back. So, all right, go team.